This is the section number 4, where we're actually going to take now a look at the actual evidence we've collected from that previous test drive.
Okay, so if you remember, this was a road test, fixed road speed, 70 miles per hour, 1800 RPM. You can see in the signal history there, we've kept the engine speed, road speed as constant as we can. We've managed to obtain a vibration. We've held the vehicle in that position. We've tried to keep all the variables to a minimum. And sure enough, T1 vibration, that's our greatest vibration on the screen. And it so happens that it's the vertical axis, so it's the red bar graph. So first order tyre speed related vibration, and it's affecting the vehicle in the vertical axis. Let's just recap on the video. Okay, so here we have the 3-axis sensor detecting vibration, fore and aft, vertical and lateral. The data's fed into the PC, keeping our engine speed and road speed constant, and T1 vibration clearly the biggest offender. So Frank, you mentioned the road test itself.
Absolutely. The big interest there for me is the fact how carefully you've maintained both engine speed and road speed incredibly stable. I think that relates back to this technique of driving and also choosing the right type of road and environment in which to do these tests so that you have as much control of the environment during the test cycle as is achievable.
I think where you can, if you can do this road test with the customer, great. It's not always possible, but simulate conditions as much as possible. Think of it as almost like a fault code, Frank, with a freeze frame data, trying to match those conditions to the code that you've obtained. Well, here we've got a complaint of vibration at a specific speed.
The biggest observation I'm picking up here from this image we're just looking at now is the way in which you've controlled very carefully both the engine speed of the vehicle and the road speed of the vehicle whilst you've been gathering this data. And I think that lends itself very much to your choice in what section of road you're going to use and the environment, in other words, traffic population on the road at the time and indeed the road surface.
Yeah, you're right, Frank. Keep variables to a minimum. We keep saying this. Remember, it's a non-intrusive measurement. Match all the conditions that the customer has complained of vibration. So again, road speed, engine speed, road surface, driving modes, suspension settings. But here, yeah, you're right, it's fixed road speed, fixed RPM, and a peak vibration in the vertical axis, T1, first order, tyre speed or frequency related vibration.
Another point I think I'd like to add here that's I think is of interest, I'm thinking now in technical terms, to do this test on the highway is far more accurate and valuable than, say, to do it on a rolling road, which doesn't simulate road movement the same. And also now you can buy ramps that can create vibration for finding one suspension and the like. And equally, that doesn't actually respond in the same way to frequency and amplitude that you would find on the actual road. So it's very much NVH is really a more focused tool than any of those other two processes.
Yeah, I hadn't thought of a rolling road simulation, but yeah, how would you ever really simulate load, the road surface, the effect of the texture of the road surface on the tyre?
Yeah.
Again, simulating the exact conditions in which the customer experiences the vibration, and an NVH will allow you to do that. So T1 vibration captured on that first road test, that was the accelerometer mounted on the seat bolt. Where do we go now? How do we pinpoint that vibration? So we'll leave the accelerometer on the seat bolt because that will always be our reference. We've got a spare channel on PicoScope. We can connect anything we want to that channel, either a microphone or another accelerometer. In this case, we know we have a vertical T1 vibration. Let's add an accelerometer to the spare channel on PicoScope, channel D, and just connect the vertical axis of that accelerometer. So if we run that animation now, you can see how we'll utilise the 4th channel of PicoScope to connect an additional accelerometer, just the y-axis, and we'll start here with the right-hand front shocker tower chassis. keep the orientation the same as the accelerometer on the driver's seat, road test the vehicle under the same conditions, and capture the amplitude. I think we can see there already that we have an increase in amplitude. So we could be homing in on the area of vibration, and I say could because we need to test all four corners of the vehicle. But clearly, vertical vibration at the same frequency as our tyre, and we've captured that more so at the front right hand of the vehicle.
So we've identified the potential area of responsibility, but not necessarily the critical location. There's still that possibility that a higher level of amplitude exists at a different location.
I think it could be very tempting at this point to assume that we've found the area, right hand front, but we must compare all four corners of the vehicle. So based on that initial road test with an additional accelerometer, let's move the accelerometer now to another location of the vehicle. So here we have the accelerometer now mounted on chassis left-hand rear of the vehicle. And you see there our vibration, we are completely off the chart there. So we are certainly zoning in on the corner of the vehicle with the offending vibration. And you saw maybe there with the dial gauge that the fault on this particular vehicle, it had already been into the workshop. It had wheel and tyre, we were happy with that. The run out was an obvious check now, brake disc, brake hub, and sure enough, drive shaft. So a word of warning here, Frank, about amplitude, and that is be aware of where you're mounting the accelerometer. Try and keep, again, variables to a minimum, front right-hand chassis, left-hand rear chassis.
And there was a serious side to the comment I made earlier about the magnetic carpet, to make sure that the surface type is as closely matched as is possible.
Yeah. Thinking about a thin section of chassis or a thin sheet steel in comparison to a chassis member with multiple layers, greater mass, most certainly you'll have more of a response from the thinner section of the chassis than you would from the thicker chassis, if you like, with the multiple layers. So it's important to be aware of that because that could trip you over. So consider these variables during your measurement.
And I guess also if there's a rubber mounting, which side of the rubber mounting you're on to keep those similarities the same as well.
Yeah. So after relocating the accelerometer to the left-hand rear of the vehicle, let's just watch this vibration form. So we're running this like a video now. We can see how this information here is increasing in amplitude. This is the black captured data from the accelerometer. We have a gear change there, 7th gear, 8th gear, and there we have it. As soon as we get to about 70 miles per hour, intense vibration. If I was to stop this capture here, quickly revert back to frequency view. Look at that. I think our original vibration was something like 40 something milli-G, I think.
Just under 48
Yeah.
milli-G, I believe. Yes.
Yeah. And then pull this marker down. We're almost double. We get to 70. Yeah. Continue to press the play. Okay, so based on these results, we can say that we've got, or we are closer to the source of our vibration, but certainly in this scenario we can see we were almost twice the amplitude when we compared the right hand front to the left hand rear. And that then begs the question, okay, we've homed in on the area of interest, what is the possible cause? Because we know with this vehicle we've had wheel and tyre check, we know that that is okay, so what does that leave us?
Right, so we've excluded the rim and the tyre, so we're looking for something at the same frequency
Yes.
as the wheel and tyre.
Yeah.
It's a T1 issue,
Yeah.
but it's not the wheel and tyre, therefore potentially brake disc, drive shaft,
Yes.
that kind of...
So we're at that point now. What measurement could we make? And as we indicated in the video that you saw, a non-intrusive measurement is Well, we know drive shaft rotates at the same frequency as tyre. Run out check of the drive shaft. Sure enough.
Yep.
Yeah.
Back to my engineering days, DTI gauge out.
DTI.
Just simply on the ramp.
Yeah. Excessive run out.
Run out on the disc, perhaps. Run out on the drive shaft.
Yeah. 1 disturbance per revolution. T1, left-hand rear of the vehicle.
And why not look for simple things like impact damage to a drive shaft, or somebody jacked it up on the drive shaft, something that's
I
perhaps even more obvious than...
That has to come into the customer questionnaire. You know, has the vehicle been worked on recently? Any accident damage? Rim damage? Hub damage? Does that left-hand rear have a new wheel and tyre installed? That's got to get alarm bells ringing.
Yes.
Yeah. Just coming back to the software quickly here. Highlight that area just to confirm that we've got T1 across that whole area. Is gear positions 7, 8, 6, and they are displayed because in vehicle information, as you mentioned earlier, Frank, in the advanced section, we can select the style of transmission, the number of gears, and each ratio for each gear, including the differential ratios front and rear. And then additionally here, pulley diameters.
Yes, yes. I think we've now clearly demonstrated the power of the software to enable to analyse the information we've gathered, together with the process of moving the various devices, in our case the three-dimensional accelerometers, around the vehicle to be able to identify not just the component responsible, but the location of the responsibility. What we'd like to do now in the next section is to move on to time domain events, which are single events where a noise occurs, where we look at them as a time domain, and that's a new method of looking at a similar problem but in a different format.